Example 1.16 is going to find a center of mass in a two-dimensional system. So we are going to have a region in the plane or an infinitely thin plate and find the center of mass. Here in this example, there is no density function. It's uniformly spread out. So if we're trying to find just the true center of an object, it's what's known as finding the centroid. So if our density function is a constant, the centroid will be the same thing as the center of mass. So let's first sketch the region that we're going to be finding the center of. We're looking for the region bounded by the curves y is equal to 2 sine 2x. So I'll just draw the necessary parts, right? That's the first hump in the oscillatory sine function. Bounded by that curve and the line y is equal to 0, so that's your x-axis. And over the interval 0 to pi over 2, so the origin will be 0, and this first root there is pi over 2. So we're trying to find the center of this region. All right, and to do so, let's take advantage of symmetry to find the easiest one, the x-center. So where should you hold this shape horizontally to balance it? By symmetry, it'll be in the exact middle of that interval, right? Because it increases at the same rate that it decreases there, right? By symmetry, the center right there is going to be the center, or rather the center of the interval will be the center for the x value. The y coordinate of the center is a little bit trickier because this object does not experience symmetry in this direction, right? It's thinner up top than it is down low. So we're going to have to play around with the y value, but we find centers of mass always by taking moments and dividing by total masses. So let's find the total mass first. And as always, we find total masses by integrating density functions over the intervals. So if we're going to integrate from 0 to pi over 2, that density function is only a function of x. So I need to multiply that density function by the length of that line that goes through my shape. And the length of that line is going to be the top curve, 2 sine of 2x, minus the bottom curve, which in this case is 0. So I'll make a small note about this. I'm taking the length of that line, that orange line, and multiplying it by this density function. That kind of gives me the density of that orange line. And then I'm going to integrate that density across from 0 to pi over 2 to find the total mass. So that's why the integral looks the way it does. Now let's run through this. We have the integral from 0 to pi over 2. The density function here in this example is a constant, so it's not going to matter. You can pull it out, or you can kind of just pretend that it's the easiest constant and just a value of 1. So we have 2 sine 2x dx. In short, if your density is uniformly distributed, you don't need to consider it. So you don't need to consider the density function here. All right, and now we are left with the task of integrating 2 times the sine of 2x. And if we do so by a u substitution or a variable substitution, you can find that an antiderivative here is going to be minus cosine of u. In fact, I'm going to go ahead and switch that back out. Minus cosine of 2x evaluated between 0 and pi over 2. So take pi over 2, plug it into this antiderivative, take 0 into this antiderivative, find the difference. You're going to get 1 plus 1, or a total mass of 2. All right, or in fact here, because our density function was a constant 1, you can think of this as total area. That's effectively what we just did. The area of the shape is 2. Okay, so I'm going to make a note. Our total mass, or our total area, is 2. And now the next thing that we need is the moment. So we're going to find moments by integrating . density functions. And then here, I won't go through the derivation again, it's further in the notes. But you end up with a 1/2 the top curve, 2 sine 2x being squared, minus the bottom curve being squared. Right? If you're interested in how that formula comes up, it's in the notes just on the previous page. So we're going to integrate that from 0 to pi over 2 because that's our interval. All right. So running through this integral, I've got a 1/2. Our density function is a constant. It doesn't matter. You can think of it as 1. 2 sine of 2x squared is going to be 4 sine squared of 2x. And then minus 0 squared is minus nothing. All right, that 4 times the 1/2 is going to give us a 2 that we can bring outside of the integral. And now we're left with the task of integrating sine squared of 2x, which there is, I don't know of an antiderivative for that. So I'm going to replace it using a trigonometric identity. You can replace sine squareds with 1 minus cosine of 2 times the variable. So 2 times 2x will be 4x over 2. So that's not calculus, that's just a trig identity. Okay, we see cancellations with the 2's, so let's get those out of there. In fact, I'm going to borrow space from this next problem. Here, our 2's are gone, and we are integrating from 0 to pi over 2, 1 minus cosine of 4x dx. So let's find antiderivatives. The 1 is going to antidifferentiate to an x. The cosine of 4x is going to antidifferentiate to a sine of 4x divided by 4. That's again another u substitution. And we will take that antiderivative between 0 and pi over 2. So after you do this, you end up with pi over 2 minus 0 at the upper bound. And then for the lower bound, you just get 0 in both positions. So it's minus nothing, minus nothing. So we really just end up with pi over 2. Again, if your calculus 1 skills are a little bit rough, pause the video, run through that with a little bit more detail, and show yourselves that you get pi over 2. Okay, so our moment is pi over 2, which means that our center of mass takes place in 2 dimensions. Right, I'm looking for an x value and a y value. The x value was found by symmetry to be pi over 4. The y value we had to actually run through the math to find because it was not obvious. And it is the moment, pi over 2, divided by the total mass, 2. So here we have a center of mass, pi over 4, pi over 4. So I can go back to this shape right there. Our center of mass happens pi over 4, pi over 4 at those coordinates.